Hi, good evening. Can you hear me?
Yes, ma'am. Good evening.
Yeah, yeah, good evening, Satyam and Ramit. Anyone else there in the meet or only both of you?
No, ma'am. Only we-
All right. So great. Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Yeah, yeah, thank you. So let us start today's. So someone is texting me or something. Okay, all right. Okay, let's start today's session. So if you have any doubts, please speak up, okay? Because I only joined from my iPad. It's hard to switch in between the chat and the recording, the screen sharing, okay? So if you have any questions, just speak up, all right? So let's start with today's session. Uh, so just a quick recap from our previous session. So in the previous session, we have discussed regarding the contents from week 4, and there were a couple of doubts, I think, like which I feel I did not answer them properly in the last live session. The first question was differentiation part, especially when you have something like direct delta function or unit step function or something with respect to these things, what happens to the differentiation. Let's quickly do some study on this in today's live session. And also someone asked me a couple of questions on cross correlation and autocorrelation, so we'll also go through them. So the agenda for today's live session, is like this. So we'll go through these things. If you have any other questions from week 1 to 4, I mean, if you have any other questions apart from these topics, also feel free to ask. Other than these topics, so there are certain topics from week 5, which I thought I'll cover from today's live session. I'll cover in today's live session. So if you have any questions regarding the following topics from week 5. So week 5 has nice introduction to systems. So end of week 4 completes the signals part. We are now entering into the systems part. So week 5 started off with introduction to systems. Yeah. And then we also saw several properties related to the systems. The first nice property is causality. Uh, and there are something known as memory systems and memoryless systems and invertible systems, invertibility, right? And stability of the systems, time invariance. These are all properties, different properties of systems. Linearity, right? Uh, Combined with both linear and time invariance, we have something known as LTI systems. And also, week 5 ended with a nice operation which you may not have learned till now or may not have heard till now, which is known as a convolution operation, which is very very important operation. So it's not at all related to multiplication or division. So it's a different operation. We will learn how to. So since our childhood we learned how to do addition, how to do subtraction, multiplication, division, but now you entered engineering, right? So once you enter engineering, this convolution is another nice nice and important operation that is required for you guys. So we will learn this nice operation in couple of lectures during this week 5. So this is the week 5 content. uh, uh, the plan for me today is I'm planning to cover at least part of the week 5 topics. How about till we do the stability and give more time to, time invariance, linearity, and convolution in our Saturday's live session. So, will that be okay? So, I'll deal till stability along with certain, questions that were asked in the last live session, like differentiation, cross correlation, autocorrelation, along with these five topics. So, the last four topics we can do in Saturday's live session. Is that okay? Hello?
Yes, ma'am.
Yeah.
Yes, ma'am.
So let's start today's live session with this differentiation thing. Last in our last live session, uh, someone asked me a question on how to differentiate signals, especially when you have something like, rectangular signal. You are seeing, so when you differentiate this some rectangular signal, uh, or maybe let me take rectangular signal only. So if you have a rectangular signal like this, rect t, uh, minus half and plus half, when you do the differentiation on this rectangular signal, what you see is direct deltas at 2 points, minus half and plus half. So I think Satyam or someone, Ritam or Satyam, I don't remember exactly, but someone asked me, like, how do we get to this point? Okay, so this was the question. There was some difficulty in finding this direct deltas while you are doing the differentiation, and where exactly do you see this direct deltas was the question. So to answer that question, the best way, or the best thing to understand and also to learn is, so there's this. So let's first understand what direct delta function itself is. So direct delta function is represented by del of t, and the nice property of direct delta function is when you integrate it over, from minus infinity to infinity dt, the area of this function is always 1. And how do we represent this direct delta function if it is in continuous time? You know, we saw that this delta function has, area 1 under 0. Suppose if you are, seeing from minus epsilon to plus epsilon, this direct delta takes a value of 1 by epsilon. Or if you're actually seeing it from minus infinity to infinity, the value it takes at 0 is infinity. So it is infinity at t equal to 0, and it is 0 otherwise. And the nice property of this delta function is when you integrate it over the entire time domain, the area under integration of the direct delta function, the area of the direct delta function within the time axis is always 1. So this is some nice important property that we already saw. I would also like to state another important property of this direct delta function, that when you integrate this direct delta function from minus infinity to t, del of tau d tau. So this would be equivalent to the step function u of t. Okay, so the way to see this is, when t is less than 0, you have minus infinity to t del of tau d tau to be 0, right? Because, when t is less than 0, del of, you are looking at the area of this delta function before 0. So delta function anyways take a value 0, other than 0, other than at point 0, right? So when t is less than infinity, this integration is 0. But when t is greater than 0, integral minus infinity to t del of tau d tau, which is also same as, integral 0 to 0 to t del of tau d tau. This is always 1. I'm sorry. So this is minus infinity to t del of tau d tau. And anyways, at 0, this takes a value of infinity. Uh, I think is this infinity or 1 over infinity? Right, this should be, um, there's something wrong that I'm writing here. Uh, or just ignore this part of the definition. Okay. So the idea that I'm trying to state is the area around 0 is, this delta function takes a value of 1. So that's the idea that I'm trying to convey. I'm missing something over here. Just give me 1 second. Or, instead of proving like this, we can also prove it the other way around. In order to prove, so all I'm trying to do is to try to prove this property of the delta function. I don't know if professor has done it in your lecture notes, but yeah, I'm trying to prove this property of the delta function. So uh, so this property is also equivalent to stating del of t is nothing but d by dt, the differentiation of u of t. This I think is some, whatever you studied in your plus 2 days. Suppose if you have minus infinity to t, x of tau d tau, if this is equal to some y of t, then x of t can be obtained by doing the differentiation over the function y of t. So this is something that we already studied in plus 1 plus 2 days. So I'm trying to prove this property of the delta function. So maybe let's try to work it the other way around and see what happens to this. Or maybe there is some confusion. I'm missing out something over here. Yeah, for a very small epsilon, the idea is for a very small epsilon, if you look at this delta function, for a very small epsilon, as epsilon tends to infinity, right? So this is how, a delta function is defined between minus epsilon to plus epsilon. And for a very small epsilon, what happens to this delta of t? So delta of t, as epsilon tends to 0, this would become infinity. So this can also be stated as a t equal to 0 or 0 otherwise. At least, is this part clear? Questions here. So delta function, has an area of 1. And the definition, how you define a delta function is, if you take a very small region between minus epsilon to plus epsilon, it takes a value of 1 over epsilon such that the entire area of this function from minus infinity to infinity is 1. Okay. And this can also be defined as something like this. And as epsilon goes to 0, what happens to the value is, this rectangle keeps on shrinking, right? And as it shrinks, it takes a value of infinity at t equal to 0 and it takes a value 0 otherwise. Is that okay? Is
So
this definition?
it is from minus epsilon to epsilon or minus epsilon by 2 to minus plus epsilon by 2.
Anything is fine. Suppose if your epsilon prime, if I define this as, let me call epsilon as some epsilon prime by 2. Anything is fine. It can even be, if it is from minus epsilon to epsilon, this should be 1 by 2 epsilon. Yeah. Is that okay?
Yeah.
So this is fine, right? So this is just the definition of the delta function. So the definition of the delta function, I'm writing it in terms of, the points. So it takes a value infinity at t equal to 0 and it takes value 0 otherwise. So now let us try to prove this property of the delta function, okay? The delta of t is nothing but the differentiation of the unit step function u of t. So how do we do this? Let's use the simple definition of the differentiation that you guys have learned during your +1 +2 days. So differentiation is nothing but this can be written as limit epsilon prime tending to 0 u of t plus some epsilon prime. I think someone unmuted your call. Could you guys mute? Yeah. So this is nothing but u of t plus epsilon prime minus u of t divided by epsilon prime, right? So this is the definition. So this is by the definition of the differentiation. Okay, this we already learned during your +2 days, right? So yeah, this is how it is. And now let t be greater than 0. When t is greater than 0, let's see what happens to this delta function. So when t is greater than 0, delta of t is limit epsilon prime tending to 0, u of t plus epsilon prime minus u of t by epsilon prime. When t is greater than 0, we know u of t is equal to 1, right? When t is greater than 0. And we are considering some positive epsilon prime. That's why t plus epsilon prime is also greater than 0 when t is greater than 0. Hence, u of t plus epsilon prime is equal to 1, right? And this is nothing but limit epsilon prime tends to 0, 1 minus 1 divided by epsilon prime, which is what? 0. So delta of t is equal to 0 when t is greater than 0. So now let us consider t to be less than 0. What happens to delta of t when t is less than 0? Delta of t is nothing but limit epsilon prime tending to 0. So I am trying to prove this, okay? So I'm trying to prove this. So if you want, you can also call this to be some x of t for now. I want to show that this x of t, when I differentiate the unit step function, I'm calling it to be x of t. I want to prove that this x of t is equal to delta of t. Okay. So maybe let me not call it delta of t now. So this is x of t. So what I proved is x of t equal to 0, x of t equal to 0 when t is greater than 0, and x of t for t less than 0, if you see, this is nothing but u of t plus epsilon prime minus u of t by epsilon prime, right? And when t is less than 0, considering epsilon prime to be really small, right? So epsilon prime is almost tending to 0. This can also be proven that 0 minus 0 by epsilon prime is 0, right? When t is less than 0, u of t is equal to 0. And also, since epsilon prime is very small, u of t plus epsilon prime is also really small. Okay. Now, what happens to when at t equal to 0? At t equal to 0, x of t or x of 0 is nothing but limit epsilon prime tending to 0, u of epsilon prime minus u of 0 by epsilon prime, right? And we know that, at t equal to 0, uh, the point where exactly t equal to 0, u of 0 is 0. So this, and epsilon prime is a really small value. So this is limit epsilon prime tending to 0, 1 minus 0 by epsilon prime, which is nothing but 1 divided by epsilon prime. So this is limit epsilon prime tending to 0, which is 1 divided by epsilon prime, which is nothing but equal to infinity, right? So what have we proved? So we proved that x of t is equal to 0 for all values of t other than 0, and x of t equal to infinity when t is equal to 0. So this function is same as the delta function. Or in other words, d by dt of the unit step function, when you take the differentiation of the unit step function, what you get is the delta function. Or equivalently, you can also state that minus infinity to t, del of tau d tau is same as the unit step function. So this is another nice important property of step function. I'm not really sure whether the professor covered it in the lecture videos, but this is another important property of delta function that you guys should be aware of. Okay. Is this clear about this property?
Ma'am, can we revisit the case when t is not equal to 0, xt is equal to 0, and t is not equal to 0?
Okay, so when t is greater than 0, right? So what is delta function? So let me recall the definition of delta function. U of t is equal to 1 for t greater than 0 and 0 for t less than or equal to 0. So this is the step function, right? Yeah. So this is the unit step function.
Yes, ma'am. For 0, ut will be 0, is it? At 0.
Yeah, it's 0. So it, if you have a slight trigger other than 0, it is positive. So in representation, the way you represent it is, because the slight variation you will not consider. So in the continuous time, it doesn't matter. So this is all right.
Okay.
Okay, so yeah, in continuous time, it actually doesn't matter whether you have like this or whether you have like this. Okay, because it's just a slight figure after 0. So I'm considering this particular definition for the step function, unit step function in continuous time. Now what happens to the differentiation of the unit step function is I'm taking the derivative. This is just the basic definition of the derivative. So this is nothing but limit epsilon prime going to 0, u of t plus epsilon prime minus u of t by epsilon prime, where epsilon prime is some positive value. So this is just the definition of the differentiation. And now what happens when t greater than 0? When t is greater than 0, u of t is always 1 because t is greater than 0. And u of t plus epsilon prime will also be greater than 0. Hence, u of t plus epsilon prime is also 1. And when you try to find the differentiation, which I am denoting by x of t, so x of t will be 0 when t is greater than 0. Likewise, when t is less than 0, I'm taking a very small epsilon prime. So when t is really small, uh, the idea is what you can try to, yeah, when t is really small, uh, you know, sorry, when t is less than 0 and epsilon prime is really small, uh, even t plus epsilon prime will be negative, and u of t will be definitely negative. U of t is evaluated at negative values of t. So this can be taken as 0, minus, or otherwise the other part is, what? Anyways 0. So this is 0 minus 0 by epsilon prime. Or in other words, if I'm not confusing you guys, what you can do is go with the standard definition. If I'm not confusing, if if you guys are okay to go through more details, and if I'm not confusing, so 1 for t greater than or equal to 0 and less than 0, if you take that, so if you take u of t plus epsilon prime minus u of t by epsilon prime, for t plus epsilon prime less than 0. So this happens when epsilon prime is less than minus t. So for the negative values of t, this happens when epsilon prime is less than minus t. So when t is less than 0, t plus epsilon prime is less than 0 only when epsilon prime is less than minus t, right? So when this happens, what happens to, so when epsilon prime is greater than minus t, what happens to u of t plus epsilon prime is 1 minus, you know, 0 divided by epsilon prime. So in that case, I won't take, epsilon prime to be limit going to be 0. So that would be 1 by epsilon prime. What I'm trying to state is when you don't take this consideration, what you could see is you can prove by doing this differentiation very slowly. You have minus epsilon prime. You can prove that this will be equal to 1 by 2 epsilon prime when you take the differentiation. Or in other words, when you take this epsilon prime to be 0, you can prove that delta of t or the differentiation of u of t, d by dt of u of t, would be equal to what? 0 when t is not equal to 0, is equal to infinity when t equal to 0. Or this as epsilon prime goes to 0. Or if you want to have that epsilon prime as it is, you can evaluate and see that d by dt of u of t would be equal to 1 by 2 epsilon prime between minus epsilon prime to epsilon prime, or 0 otherwise. I hope this is clear. I mean, if you guys don't want to see the zeros and infinities, if it is, more confusing, you can evaluate any two things. So it's just playing with the values of t being greater than 0, t less than 0, and all you know is when t is greater than 0, u of t takes a value of 1, and when t is less than 0, u of t takes a value of 0. And be it in any definition, you end up with what you have over here.
Ma'am, this half epsilon dash one is not clear. Means how does
Which one?
half comes in play? At
Which
the
one?
end, you have written d by dt of ut is equal to. Can you scroll down, please?
Yes.
Yeah, at the end, the last one definition of
Uh, so
differentiation ut.
if I see it correctly, when you have epsilon prime gap, what you can prove is not really sure. Maybe, or I'm confusing you guys more. Just let's stick with one definition. When the things are not clear in my hands, maybe I should not confuse you guys. So let me, but at least I conveyed the idea, right? So I'm trying to convey is this property of the delta function, and at least I think I have done a decent job to convince you guys. If you want a nice derivation for this, what I can do is I can write this derivation up for you guys and share it with you after this class. Will that be all right? A different derivation, so cleanly.
Sure, ma'am. Yeah.
Yeah, will that work? So for
Yep.
now, but the idea that I'm trying to do is there is another property for this delta function, and this is what it is. And yeah, when you have this rectangular function, so there's also another important part to this. So d by dt of u of at plus b would be d by dt of u of, so if I, so what happens to this is when you have something like this, what you get is sine of A times delta of t divided by mod A. So that is what it is. So this is also another nice thing to prove. The reason for this is, so uh, d by dt of u of at plus b, what happens to this is, so this is equal to del of at plus b times d by dt of at plus b, right? And this is same as we know that del of at plus b is nothing but del of t by mod a times d by dt of at plus b, which is del of t by mod a times a, which is nothing but, so a can be written as sine a. Sine is, if a is greater than 0, sine of a is 1. If a is less than 0, sine of a is minus 1. So this is sine of a times mod a times del of t by mod a. So this is simply, uh, I think this is del of t plus b by a. Alright, so yeah, I think this is what. So this is del of t plus b by a divided by mod a, which is nothing but sine of a times del of t plus b by a. So this is something I think Professor discussed in your lecture 6. Week 4. So you guys also can refer to this. So yeah, so this is also another nice property for the delta functions. So d by dt of u of at plus b would be sine a times del of t plus b by a. So that is another nice thing to remember. Now, what happens to this rectangular function is, so this is minus half to plus half rectangular function of t. So this rectangular function of t, if you see, it can be written as summation of some unit impulses. One function, impulse function, is this impulse function, and the other other unit function is this unit function. So if you add these two things up, what you get is the rectangular function. So this can be written as u of uh, what, minus t minus half, minus t minus half, right? So what is this function? Can you guys help me? So this is minus t minus half, right? Or minus t plus half. Is that correct?
Why would it be minus t?
Hmm?
Okay,
Uh,
yeah. It start. Okay, I got it. Yeah. So minus
yeah,
t plus. Yeah, that's right.
yeah. And what would be this? So this is u of uh, t. mm,
It can also be written as u of minus t minus half.
Is it u of minus t minus half, or what is u of t plus half? So u of t plus half is this. So this is u of t plus half, where you have minus half. Now when I take u of minus t plus half, that would be simply this. Okay, right. And now what I want is minus half, sorry, plus half to this. So this is u of t minus half. All right. So this is u of minus t minus half. All right. So this is u of minus t minus half, right? So when you add these two signals, when you subtract these two signals, so this is u of, so, and maybe I have to subtract, right? Or also I can write it as, yeah. So this is u of minus t plus half minus u of minus t minus half, right? So when I differentiate these two signals, what I get is this is sine of A times del of t plus half minus sine of A is 1, right? So A is minus 1. So this is sine of minus 1 times del of uh, minus t minus half, right? So which is nothing but minus 1 times del of minus t plus half minus minus 1 times del of minus t minus half. So how does this signal look like? So again, del of minus t plus half is what? Del by del of t by mod a, if I remember correctly. So again, a factor of minus 1 would be coming. So at minus half, we have 1, and at plus half, we have a value of minus 1. Is that all right?
Can you repeat
Hello?
that, please?
Okay, so del of
Just the last
at
step.
is del of t by mod a, or sorry, I think so. Is this the reverse direction? So this is nothing but minus 1 times del of minus t plus half minus del of minus t minus half. Sorry, plus
Plus.
del of
Yeah.
minus t minus half, right? So now I
Yeah.
have to plot these signals. So what happens to del of minus t plus half? So del of minus t plus half is, so this is my del of t, it takes a value. So we have 1 over here. Now what is del of minus, so del of t plus half? So t plus half is at minus half, we have a value 1, right? I need some help from you guys. I'm getting
Yeah. Yeah.
confused. So this is right. And then what happens to del of minus t plus half? So it's just a shift,
You're right. Um,
right?
amplitude reverse. How does minus t affects, ma'am?
How does?
Minus t. We have minus t, right? Minus t
Yeah,
plus half and minus t minus half.
right. So what I'm see, okay, let me plot it from the beginning. So at least here till here, this is okay, right?
Yeah.
So
This
what we
analytic
have is del
derivation
of
thing.
minus t plus half
Yeah.
plus del of minus t minus half. Let us plot these two signals separately and try to add them up. So let us first try to plot del of minus t plus half. So what is
Okay.
our del of t? So our del of t is at 0. We
Yeah.
have a value 1. So this is our del of t. Now what happens to del of, so remember our, so we know how to go from x of t to x of at plus b. So what are our points? First shift by b and then scale by a, right?
Yeah.
So
Yeah.
our a is minus 1 and b is half. So shifting by positive b is nothing but what? Subtracting the time axis by minus half. So At minus half, we have 1. So this is del of t plus half, right? The signal is, the signal is advanced by half. That is what we mean by this, right?
Yeah.
So this
Yes.
is shift by B. And now then scale by A. So scale by A is minus 1. What we have to do is divide the time axis by A, right?
Yeah.
So what we get then? So, so del of minus t plus half is, right? Is that okay?
Okay. Okay. Yeah. Yeah.
Now what we have is a negative value for del of minus t plus half. So we have to multiply this by minus 1. So minus delta of minus t plus half is that okay?
Yeah. Yeah. That
So
makes
this
sense.
is fine. And then
Yes.
now del of minus t minus half, if you just go through it, it would just be simply at minus half, we have a value of 1. And now when we add these two things up, what you get is at minus half, you have a value of 1, and at plus half, you have a value of minus 1. So this is the differentiation of the rectangular signal. Okay. So the property, all you need to use over here is d by dt of the unit step function is the impulse function, or equivalently, integral minus infinity to t del of tau d tau is a unit function. So this is a nice property. So wherever you have step functions, when you differentiate them, what you get is an impulse function. Is that okay?
Yeah.
Yeah. Can you take question from the week 4 grading assignment?
Could you tell me the question, what that question is?
Yeah, two questions were there on integration of a given signal xt into delta t minus tau.
Sorry, could you repeat? I missed it. Week 4, right?
Yeah, week 4. Yeah, week 4.
Graded
I think.
assignment.
Yeah. Yeah.
Question numbers, please.
I think it's 8 or 9, something in that. 1 minute, I'll just tell you.
Oh, week 4 graded assignments, they just use the property that we discussed in our earlier live sessions. So, what is that property? So, del of T naught
Yeah.
times, sorry, when you multiply the function uh, del of T with x of T minus T naught. So, this is simply del of T naught times x of T minus T naught.
Yeah.
This is something that we discussed earlier. So those graded assignments just use this property. I think we also did couple of questions using this property. So when you have integration of minus infinity to infinity,
Yeah.
so let me take an example.
5.
What?
Can you take 5? 5
So
number. Yeah.
del of t sine uh, omega naught t. Mm,
No, you take the same example, no, the 5 number. X
Are
tau.
the solutions given? Week assignments are submitted, huh?
Yeah, it's submitted. Yeah, yeah. It is
All right.
deadline
So,
already crossed. Yeah.
okay. So, which question is that? Eighth or ninth?
No, 5, question number 5 and 6. Sorry, no, no. Only
Question.
question number 5, then question number 7. Yeah. First, can you take question number 5?
Okay. Question number 5. So, minus infinity to infinity,
Yeah.
x of tau, del of t minus tau d tau, right? So, this is same as, so this can be written as minus infinity to infinity, x of tau, del of minus tau plus t d tau, right?
Yeah.
So now let me call my tau minus tau as some t prime. So d minus d tau is dt prime, right? And as tau goes from minus infinity to infinity, t prime, which is equal to minus tau, goes from infinity to minus infinity, right? So this is same as infinity to minus infinity, x of tau del of t prime plus t minus dt prime. Is that okay?
Yeah.
So
So
this is again same as integral minus infinity to infinity minus x of tau del of t prime plus t minus dt prime, right? So
no, I
now,
think minus won't be there, no, because you have flipped the limit.
oh yeah, I flipped the limit, hence the minus. And dt prime, so d tau is minus dt prime, so that minus will be there, right?
Okay, okay, yeah, you're doing second.
So this is same as minus infinity to infinity x of tau del of t prime minus minus t, right? Dt prime.
Yeah.
And what is my uh, okay, I think okay. Is the question?
I think the answer
Yeah,
maybe
I think the answer is wrong. I think the answer is wrong. Yeah, I agree. So this happens only so that there should be some other property. Suppose if x is even.
yeah.
If x of t is an even signal, then the given answer is correct. Okay, we will do the revaluation for that question. Okay, so if x of t is even, what happens is x of t is equal to x of minus t. Then what
Yeah.
happens to this part is, so this is same as minus infinity to infinity, x of minus t prime del of t prime minus of minus t dt prime. And when x is an even signal, this is x of t prime del of t prime minus of minus t dt prime, which is same as by the property that I have stated earlier. This would be minus infinity to infinity x of minus t del of t prime minus t prime plus t dt prime. And this is same as, so I can get out the x of minus t part, integral minus infinity to infinity del of t prime plus t dt prime. This is 1 and this is x of minus t, which is also equal to x of t since x is even. I think the property that x is even is missing. We'll do the revaluation for this question. Yeah, thanks for letting me know.
But
Question 5.
yeah, but we have ticked x tau, so that will be wrong. Huh?
So x tau is the answer, x tau is wrong. Yeah.
So,
No,
but
no. The question is correct. The question is correct, but it maybe we should also have stated that x of t is an even signal.
okay,
That condition is not required. That will be true even for odd signals, means irrespective of how the function
Is
is.
it? Is it?
I mean,
So can you
I
do
did,
that?
I didn't do it in this derivation manner. I just I mean, how I approached it is, in case if a function xt is multiplied by delta function,
Mm,
and then we need to take the integration over the entire time domain.
mm,
I My understanding is from the lectures is that we just need to take the function's value uh, at that point where delta function is not zero or is infinity.
uh, so right. So you are telling me. So this is x of tau del of t minus tau d tau,
Yeah,
right?
yeah.
So what
So
you're telling me is integral minus infinity to infinity x of t del of t minus t naught dt. is x of t naught, right?
Yes. Yeah.
So this is very different. So this is slightly different from this, if you see. Because, so if I have to write it in terms of this, so let me not, to not get confused, let me call t's as t primes over here. I think someone unmuted. It's giving me some noise. Can you mute the, yeah, thanks. So if you want to write this in terms of this, so let me call my tau as t prime. So this is x of t prime del of t minus t prime dt prime. So it's slightly different in this sense. Okay. And if you want to just, replace these things, uh, so then, you know, uh, it's not very evident that when you do a shift x of t prime del of t naught minus t prime dt prime, is this equal to x of t naught, is the question that we are looking at. Okay, so what we stated just now is it might be equal to x of t naught when x is an even signal.
No, what I think that if there is no integration, then this condition may be right. But if there is integration over infinity to infinity, then the
Mm.
convolutions laws comes in the picture, correct? Because we are sliding delta function over
Let
the
us let
xt.
us let us not even think about the convolution. We didn't even go to the convolution part yet. So let us just try to only think in the, so this is equal to t naught because in this sense we can write this as minus infinity to infinity x of t naught del of t prime minus t naught dt prime, which is nothing but x of t naught times integral minus infinity to infinity del of t prime minus t naught dt prime, and this we know is equal to 1, hence this is equal to x of t naught. But here in this case, if you see, so this is minus infinity to infinity x of t prime, and this t naught I'm calling my minus t prime as some, call it t double prime. So this is t naught plus t double prime, uh, d dt double prime. So when I do the differentiation and interchange the integrations, what you get is this. Okay, so this is same as integral minus infinity to infinity x of minus t double prime del of t double prime plus t naught and dt double prime, or maybe it is, so yeah, yeah.
No,
Okay,
but
so
in the question, t prime and t double prime is the same parameter, na? In the given question, it is a tau, correct?
no, no, they're not the same parameters. So that's what I'm telling. So it's the negated version. So maybe you guys have to just carefully look at it again. So it's not the same. It's not the same. So what we know is integral minus infinity to infinity x of t prime del of t prime minus t naught dt prime is x of t naught, or what we also know is x of t prime del of t prime minus t naught is x of t naught. This is something that we know. Okay,
Yeah.
in the question what is given is minus infinity to infinity x of tau del of t minus tau d tau. So this is the question that is being asked. If you call your tau as
What
t
if
prime,
we,
so
sorry
this
for
is
interrupting
integral.
you.
Let me just finish off writing. So if I call my tau as t prime, this is x of t prime del of t minus t prime dt tau. So calling my tau as t prime and t as t naught here. So this is slightly different version from what you have here.
I agree, ma'am. This is slightly different, and I think that that difference or that confusion will not appear if we substitute t minus tau to be, we are differentiating with respect to tau, right? So
Yeah.
t minus tau to be minus x.
So if I had given t minus tau to be,
Minus x.
Okay, if I call t minus tau to be
or
minus
just
x,
x,
now what?
just
Okay,
x.
so if I call this to be x, then this is equal to
So d
minus
tau
d tau should be dx. Okay, so this would be integral minus infinity to infinity x of t plus x del of x dx, right?
minus dx.
Yeah, I even interchanged the
So with this
integration
condition,
terms.
it will become zero actually, no? Because delta x can be at zero also in that interval, correct?
Hmm?
I mean, if you
Minus
go with
sign.
this equation, then delta x can be zero between infinity to infinity, and it becomes zero. I mean, x at
So,
zero. Yeah.
yeah, so his point is now when we try to look at this, so uh,
Minus sign will also come, right? For
uh,
minus
e-
d tau.
there's no
Dx
minus
is
sign. There's
dx is
so
equal to minus d tau.
uh, dx is equal to minus d tau, but x is going from minus infinity. Sorry, when tau is going from minus infinity to infinity, x goes from t minus infinity to t plus sorry, t plus infinity to t minus infinity, right?
Yeah.
So this would be
Okay.
t plus
Limits.
infinity t. Yeah. So this is not actually the same. You can work it out, and it won't give you the same answer that you are looking at.
So what would be the answer for this question? I mean, in the given scenario,
Uh,
what would be the answer?
The answer, like at least if you want one answer from your options, I think we may have to give some other property stating either x is even or some other thing. So the question is not very straightforward at this point. So yeah. So provided x is an even signal, what you can prove is it is equal to x of t.
Okay.
Otherwise, you may not be able to prove it to be x of t. You may have to uh, end at this point. So, um,
Can you look question number 7? Similar thing is I'm able to see because question number 7.
yeah, just a second. Or it is equal to x of minus tau. Maybe it is equal to x of minus tau. Or yeah, maybe I'll look at this question. So there is some confusion in this question. Question 5, we will do a revaluation. Okay. Question 7. Okay.
And one more thing from geometrical point of view, that question number 5, can you try to interpret from the graph? Can you explain with respect to graph?
Yeah, sure. Just give me like a moment. So question 5. Okay,
Yeah.
so what is so x of tau can be any signal. So x of tau is some any signal.
Okay.
Now we have del of t minus tau. So
Should
first
we,
let us, so this is del of minus tau plus t. So don't get confused with this t. If it is confusing, let me call it to be a. Okay.
yeah.
So what will be this del of, so who is talking? Is it, just want to know.
No, I'm only speaking. I mean, there's no other one is talking here.
Yeah, who is that? Forgot the name. No, could you
Prabhan-
tell me your,
Prabhanjan here. Yeah.
Prabhanshan. All right. Okay. All right. So yeah. So what is del of minus t plus a? So del of minus t plus a. Could you tell me what it would be?
So we have to reverse the signal on the negative side, I believe. Then we have to advance the signal further by plus
I
a.
just told you the steps, man. I
Yeah.
just told you the steps. You have to first do the shift and then scale, right? So
Okay.
what is the shifting? So shifting gives you at minus a, you have a
Yeah.
value 1. And when you reverse the time at plus a, you have a value 1, right? So this is your
Yeah.
del of minus tau plus a, right?
Yeah.
And what happens when you multiply these two?
Yeah. So
So
if you
this is
multiply,
your this is your x of tau. So what happens is what you obtain is x of at x of a, right? When you
Yeah.
multiply these two signals at x of a, so only at a, you have a value of 1 for del of minus t plus a, and for x of tau, that is, uh, so y of tau is integral minus infinity to infinity x of tau del of a minus tau d tau, which is same as integral minus infinity to infinity. So this is x of a d tau, uh, right?
Yeah, then it will become XA, correct? I mean, the
Yeah, this becomes xa. Yeah.
XA is nothing but XT. What is, we have assumed like A is equal to T.
Uh, yeah, maybe. So it is equal to x of t. Okay, in the plot wise, but uh,
So with that, it is answer will be, I mean, XT, the first option, I think, yeah.
okay, okay. I'll verify this question, but there's some confusion with the derivation. I may have to verify it again. Yeah.
Okay. Can you look on seven number?
So what is the confusion here?
Here, I mean, the answers is right answer is given XT, but I mean, X0, what I see, because tau is at 0. So,
So
yeah,
this is same as minus infinity to infinity.
yeah,
Uh, x of, so this I can write as, let me call some u is equal to t minus tau. Okay. So in that case, what happens is this is same as x of u del of uh, t minus u du, right? So from the previous problem, this is equal to x of t. If your explanation for that is correct, then this would be
yeah.
equal to x of t.
So this will also be equal to X of T. Okay.
Yeah,
So I mean that is answer given actually XT. So in both the cases it is XT only.
yeah.
Okay. But in the tau axis, I see the delta is at 0 because the tau. Then if you multiply with any x signal, it's supposed to be at 0. I mean the 0 origin. No? It should be at 0 actually.
Could you repeat it again, please?
I'm saying suppose without integration we are writing some functions like delta tau into x t minus tau. So what will be the output of that signal?
Sorry, I didn't get your question yet.
uh, for a general multiplication of two signal where delta tau into x t minus tau delta
Delta
tau
tau into,
into x t minus tau.
yeah.
So in this case what will be the output? It is x0 or xt?
I think you're trying to teach me or something. It
No, I'm
feels
just
like you're
because
trying
I'm
to
getting.
teach me,
No,
but
no,
that's
sorry.
okay.
Yeah,
Yeah,
I'm
but
not
that's
trying to teach
okay.
you because I have some confusion, so I'm just trying to
Yeah, yeah.
clear my
So,
confusion. Yeah,
yeah, so when you try to, so this is your delta tau function, right?
yeah,
So it's 0. And when you plot your x of t minus tau, so this is same as x of minus tau plus t, right? So so let me call this x of minus tau plus t as some y of tau. Okay.
yeah,
So when I multiply these two, what you get is y of 0, right? Because
yeah,
so this is how your function y of tau looks like. Sorry, this should be y of tau and this should be tau. When you multiply these two, only at 0, your delta function takes a value. So when you multiply these two, Uh, Honestly, this is okay. That's fine. So
So
this would be, I mean, this is not exactly the same. Even here, the problem is delta function do not take a value one at a particular value. You understand that point, right? So when you integrate the delta function from minus infinity to infinity, the area of the delta function is one, but it need not take a value one. So that is my
okay.
confusion. So that is not very. So when you multiply these two, it will not give you y of 0. You understand why it is 2, right? Because delta of 0 is not 1. But the area of the delta function is 1, right?
Correct. So,
So
no,
so so delta, but what you can say is delta of t times, sorry, sorry, x of t times delta of t minus t naught is same as x of t naught times delta of t minus t naught. All you can say is only this, but what you're trying to make me prove is x of t times delta of t minus t naught is x of t naught. You're trying to make me prove this, but this is not correct. That is what I'm trying to say.
but
But
at the some point,
but you
professor
can
also,
but you
hello.
can prove minus infinity to infinity x of t times del of t minus t naught dt. This is equal to x of t naught. This
See,
is right.
I through the lecture when we went through, I think professor also has mentioned that x the second which we have written equal to x t naught. I mean the
So
t naught. Yeah,
this.
yeah,
You
yeah.
mean
That
this?
no, no, the top one, top one.
You mean this? Did he mention somewhere about
Yeah,
this?
he has mentioned in the lecture at some point that this will be equal to that.
That will not be true. Could you tell me which lecture and at what point? You can email me that. But that is not true. Because delta function, all you know, so delta function will not take a particular value 1 at t equal to 0. That is not true. What is delta function? Delta function is when you integrate it across entire time axis, the area under the integration is 1. And how do you get to this? So this you get to this because you have this property of delta function, delta of t minus t naught dt. Now this is independent of t, which you can write as x of t naught minus infinity to infinity del of t minus t naught dt, right? And if you call this t prime, this is same as minus infinity to infinity del of t prime dt prime, and this is equal to 1. Hence, this is equal to x of t naught. But how would you prove this? Can you tell me? How would you prove x of t times del of t minus t naught is equal to x of t naught? Can you prove this, please?
Actually, see, I also have doubt and confusion because of this. So that's the reason I'm trying to just. So you understand the
Yeah,
doubts are like this because we are not able to. When the integration is coming in the picture, I mean, without the integration, then how the values are changing.
yeah,
So we are not able to visualize actually into intuitive way that what is happening behind the multiplication of two numbers within the integration.
yeah,
So that's the reason I was asking. With I am not trying to teach you. Basically, you know better than me. Sorry for that, but
yeah. So that's okay. That's all right. So all I'm trying to state is x of t times del of t minus t naught is not equal to x of t naught. But what you can show is this, but not this. Okay. So that is what I wanted to convey. Don't get confused. So delta of t is not this function. If you guys are mistaking it, I request you guys to not get confused. So this is not this function. Delta, all you know about delta function is minus. So the area. So delta function, the area of the function is concentrated around 0, and the area of that function around 0 is 1. Okay, so that is the definition of direct delta function, but that is not equal to this function. So Prabhanjit, so whatever you're stating, the timestamp, could you please email me so that I'll, check the lecture if there is some mistake
yeah,
over there.
I'm checking out that only. I'll show you the frame and time also. Yeah.
Yeah,
Ma'am,
yeah, yeah.
Ma'am, professor in the lecture he said the integration of delta t minus t naught and xt which is equal to xt naught.
Yeah, so this is true. This is not true. Definitely, this is not true. This is true. Okay. So I hope you guys, so just to summarize on the direct delta functions, okay. So we have couple of important properties. So the area of the, so we represent it by del of t. Area under the delta function is always 1, okay. Or if you take it with some less range, then, to make the area 1, the integration from minus epsilon to epsilon del of t dt is 1 by 2 epsilon. So this is one important property of the delta function. And the other important property is x of t times del of t minus t naught is same as x of t naught times del of t minus t naught. This is another important, very important property of delta function. And the relation between the delta function and the unit impulse function. So when you when you take the derivative of the unit impulse function, what you get is the direct delta function, or equivalently, when you integrate the direct delta function, you get an impulse function. Okay, so I gave a quick proof on this part today, but I can give you a clear written proof. I can send it out to you guys. Maybe I'll send to any one of you, either Ritam or Satyam, and you could pass it over your WhatsApp group. Or also I can give that proof in the next practice assignment. Okay, so this I'll do, but I think I gave the quick idea. You have to use the definitions of unit step function and the definition of differentiation to get to this proof. There may be some calculation mistake which I have done, but the idea is correct. Okay, so these are
And,
certain properties of delta functions.
and
Yeah.
can you give some property for the I mean the within the integration when there is a different function with the delta? I
Within
mean
the
I mean the kind of questions we are solving just now 5 and 7 the similar kind of property.
Prabhanjit, have you attended last live session? I don't think you attended the live session where we
Yeah.
solved clear examples on delta functions, but the recording is available. We
Okay.
have done several examples. I think other students are very much comfortable with those questions.
Okay.
So we have done several examples, like when you have minus infinity to infinity del of t plus 1 sine uh, sine pi t dt. So how to solve this? All such examples we have done in our earlier live sessions. So the recording is available. I advise you to please go and watch that live session once.
No problem. I'll have watch.
Yeah, because it's the same thing. We use the property of this, and yeah, we have done that in the earlier live sessions. So one of the live session, we concentrated only on solving the delta functions thing.
Okay. I'll go through that.
Okay, because today's live session is on week 5 content. I'm only doing this because someone asked me how to, how does the differentiation of unit function is a delta function in the last live session. That's the reason I took up this topic, but this topic was already covered in the earlier live session. Okay.
Yeah.
Yeah, thank you. I'm sorry, but if you have more questions, please feel free to email me. I'm running out of time. I also should, try to cover week 5 topics, right? So in the interest
Yeah.
of time, I'm just going ahead, okay? So the other question that someone asked me was, could you talk more about autocorrelation and cross correlation? So I'll quickly talk on this and then I'll go ahead. So autocorrelation between any two signals x of t and y of t. So what do you mean by this correlation? Correlation is something, uh, it's correlation. So if two things match, then they correlate, they're correlated. So for example, if you take uh, uh, the temperature and the humidity, today. So at time today, so maybe at 10 a.m., the temperature is 30 degrees, humidity is less. At 11 a.m. today, the temperature is 33 degrees, humidity is less. At 12 a.m., it is 34 degrees, less humidity. Likewise, you can write some data, and if you want to look at how correlated these two variables are, temperature and humidity, uh, maybe at the end of the day, looking at this data set, one can say if the temperature is less than 30 degrees, then the humidity is less. Or if the temperature is larger than 40 degrees, the humidity is more. Something like that. You can, by looking at this data, you can, at the end of the day, you can correlate these two data variables, and you can say something about that, right? So if at all, if you don't have the temperature measurement meter, if you have something to measure humidity, just by measuring the humidity, you can say, okay, maybe the temperature could be in between 30 to 35, right? So you can do that only because these two variables are correlated. Suppose if they are not at all correlated, for example, you know some random things happen with humidity and temperature. Irrespective of the temperature, this is either high or medium. So irrespective of the temperature, the humidity, if it keeps varying, then one can say, okay, like, humidity is not at all depending on temperature. Randomly things are varying. Okay, in that sense, we can say the two variables are less correlated. Okay, but how do we measure this correlation? So suppose if you are given two, so here I am talking about two variables, but suppose if you are given two signals, x of t and y of t, how do you measure how correlated they are? Or if you're given two random variables in this sense, how do you, so there should be some measure, right? Maybe you can say 90% they are correlated. In place, 90% of the time, if you have humidity in hand, you can also tell about the temperature. Or if you have 90% of the time, if you have temperature in hand, you can also tell about the humidity. So how do you measure that correlation? Measure of correlation in between two signals is given by this autocorrelation function. Okay, so how is this defined? So autocorrelation, so we are defining it using this random variable rx, y. So this is nothing but integral minus infinity to infinity x of t plus v, y of v dv. If I remember the definition correct, this is what it is. Correct me if I'm wrong. Is this correct? Anyone? Hello? Am I still in the talk?
What is the question? Can you repeat it, ma'am?
Is this definition correct, or did I write some mistake over
What?
this? So if I
Uh,
remember, properly, this is what it is given. So the autocorrelation function is defined in this way. So is the definition correct? You can check it up. It's there in your notes. But yeah, all I'm trying to give is the idea. So the autocorrelation function is defined in this manner. And what is cross correlation? So cross correlation is the correlation in between the signal that is there. The within signal, what's the correlation? That is defined by r xx of t, which is nothing but minus infinity to infinity x of t plus v, uh, x of v dv. Okay, so this is defined as the sorry, this is cross correlation and this is autocorrelation. So autocorrelation is the correlation between cross correlation is the correlation between any two signals, and autocorrelation is the correlation within the signal. Okay, so these are like the definitions. So how correlated the given two signals are, that is what we are measuring. So what is autocorrelation is when you shift the signal. So you have some signal x of t, and you're shifting the signal in time, and after shifting, how correlated is the signal with the signal that is not shifted. For example, if I delay the signal, how correlated is the delayed version with the original version? That is what is given by the autocorrelation function. But the cross correlation signal, it's the measure of correlation between two different signals, x of t and y of t. Okay, so this is the theory behind correlation of signals. So it measures how correlated the two signals are. And if you are measuring the correlation between, like, correlation within the same signal. What it means is you're looking at how correlated when you shift the same signal in time. Suppose if you shift, how close is the signal to the original signal is given by the autocorrelation function. Okay. There are also other nice properties of this autocorrelation and cross correlation, which is explained, which was explained in detail in your class notes. For example, what happens to the periodicity of the correlated signal, and what happens to the even properties of this correlated signals, are they even or odd. All these details were spoken in your lecture video. If you if you want to know more about this sort of correlation and cross correlation, you can visit that. But the idea is correlation is the measure which tells you how close the two signals are. If you're measuring the closeness between two different signals, it is known as the cross correlation. If you're measuring the closeness within the same signal, which is shifted in time, then that is known as the autocorrelation function. Yeah. Any questions regarding this? Hello?
No, ma'am.
No,
No.
no question.
Yeah,
No,
if you
this quiz one is going to be till week 4 for this one.
week 4, lecture 6.
No, I'm saying the
But
quiz one till what week it will cover? Quiz one, yeah.
week 4.
Week 4, okay.
Yeah.
Okay.
All right. So I'll go to week 5 content. Yeah, but there are a couple of things that I have to check. Questions 5 and 7 from week 4 graded assignment. I'll check these questions. If there are, if there is something wrong with the questions, I will post it. I'll announce it on your groups. Or if at all there is nothing wrong, I'll also post a solution. We'll try to reevaluate this question. If there is mistake from our side, we would like to give 2 marks for these 2 questions. Okay. So yeah.
And this week assignment deadline can increase, possible to increase. I mean, till because we'll have exam and we have to work on.
Yeah. I'll discuss that with the team and I'll let you know, guys. Okay.
Yeah.
Right. Okay. So, do you guys want me to explain week 5 content, or should we discuss more on content till week 4, since your quiz is coming up? What
No,
would you prefer?
I think we let us focus on the quiz one content and revision actually, because all the courses are happening for that only, that going in the similar
Yeah,
way.
I would like to take out regarding this. So, how about the other guys? What do you guys think?
Revision.
Hmm? Revision. Okay.
Yes,
Uh,
ma'am. Revision.
okay. So yeah, so I think I have already done enough videos on giving summary on the week 1 content. If you have any specific questions, we can discuss those questions. Yeah, I'm here for another 40 minutes. If you have any specific questions, we can definitely discuss those questions.
So, I
Uh,
mean, we are going from week one revision, or how you plan?
yeah, no, there's no revision. I think I already gave enough summary in the earlier live session, so I'm not going to give summary again. If you guys
Okay.
have any specific questions, yeah, I can go through them. Uh,
I think then you have to give us time to work out and come with the questions.
as in,
No, I'm saying I mean, we have a question, but we have not summarized the question. So maybe when next session we'll ask that. Yeah.
Next session is on Saturday, right? When is your quiz? Monday?
Yeah, can you keep on before that? I mean, not on Saturday. I think.
Uh, uh, that I have to see, but yeah, I'll check and I'll let you know.
Yeah.
Uh, yeah, I think to answer your question 5, I'm sorry, I think I'm confused earlier, but it's just direct, right, from the property. So the given signal is x of tau, del of t minus tau d tau, right? Hello?
Yeah, I'm listening. Yeah.
Yeah. So just from the property that I have stated earlier, this is same as x of t, del of t minus tau d tau, right?
Yeah.
Sorry, this is same as this, just from the property that I have stated earlier, right?
Yeah.
So now what happens to this? So this is same as integral minus infinity to infinity x of t del of t minus tau d tau, correct?
Yeah.
So now since x of t is independent of tau, I can remove it. So this is x del of t minus tau d tau, correct?
Yeah.
So now let me call this t minus tau as some tau prime. You can prove that this is equal to 1, hence this is x of t. So it's straightforward, right? So
Yeah.
I
Yeah.
I think I confused you guys a lot. I got confused and I confused you guys. So yeah, it is yeah, just by using this property.
Okay.
And I
Yeah.
think your seventh question also will follow from this property.
Okay. Yeah, I think we'll try that one. Yeah.
Is that okay? So
Yeah.
the only things that you have to remember in delta functions, these three important properties. That's all. Nothing more. If you know these three, I think you can solve any problem with respect to the delta functions. Is that okay?
Yeah. Understand. Thank you.
Yeah. So yeah, I'm sorry. I think I confused you guys a lot today. Really sorry. Any specific topics you guys would like to discuss or facing some difficulty in solving?
I think can you take a topic on energy and power of the signal and their significance? If you can briefly, you can tell that will be helpful for us.
Definitely, but I would also like to take the voting from other guys because
Yeah.
uh, people like Satyam and Ritam, they already heard enough with respect to energy and power, and also it is there in all other live sessions. So yeah, the summary on energy and power is already there in the previous live sessions. Okay, guys, like I also need opinion from you guys. Other people, please speak up. If everybody would like to learn about energy and power, I can speak more on it. But just to give some introduction to Prabhanjit, what exactly is your question on energy and power, Prabhanjit?
No, I see. I wanted to know the understand the significance of energy and power in the signal analysis. So that point I wanted to understand.
What do you mean by the significance of energy and power?
Significant in the sense that suppose a signal I have which is having some finite energy, and another signal I have with some finite energy, and one signal which is have the higher finite energy compared to another one. So how do I interpret that particular signal with respect to the? I mean, is it going to consume more energy to transfer, or is it the strength wise it is high? So those things I
Pravanjit, but
want. Yeah,
just to not offend you, you're
yeah.
speaking out of the subject. You're
Okay,
asking questions which are going out of signals and systems. I already told you, so if you want to have discussion or, you know, people over here doesn't even know what you mean by transmission of the signal first in the place. Okay,
okay.
so those things come in the later subjects. You're talking in depth from the other subjects, which I would not like to answer. If you have more questions related to other subjects, you can email me, but not in the live session because others also should be able to follow them, right?
Yeah, yeah. I mean, see, in terms of when going through that, I was just, I mean, this is thought
Yeah,
that,
so
yeah.
this live session is solely meant for signals and systems. And if you have any specific questions related to the topics covered in the lecture videos, okay?
Okay,
So
I mean,
these
even
live sessions are only for those things, but not for anything other than lecture videos. If you, yeah,
no, if it is out of scope, then I think no problem. I mean, this okay.
yeah. I mean, I can discuss them separately on email, but not in the live session, in the
No
interest
problem.
of others. Yeah,
Excuse me,
yeah.
ma'am. I have a doubt in the. I cannot understand the GA question 10. Can you explain?
Could you repeat the question again?
Question graded assignment 10th question.
Graded assignment. Which graded assignment, Ramit?
Week 4, ma'am.
Week four. This. All right. Uh, yeah. This I think we already discussed in our. No, I think we did not. Okay, we'll go through this. Right. So this is. Sorry. So there was a printing error which we discussed in our last live session. I hope, Ramit, I think you only posted it on group, right? So it takes
Yes,
a
ma'am.
value -1. Okay. So the question now is to find, this is also the x of t signal. So you're asked to find integral minus infinity to infinity x of t del of t plus 1 minus del of t minus 3 dt, right? So how would you do this? So this is minus infinity to infinity. So integration is linear, right? So we can just split the integration into two parts, del of t minus 3 dt, right? Is this okay, Ramit?
Yes, ma'am. Yes, ma'am.
And now what we know, x of t times del of t minus t naught is same as x of t naught times del of t minus t naught. This is what we know, right? Here our t naught is -1 and here our t naught is 3. So what happens to this? So this is minus infinity to infinity x of -1 del of t plus 1 dt minus integral minus infinity to infinity x of 3 del of t minus 3 dt, correct?
Yes, ma'am.
And now this is x of -1 del of t plus 1 dt minus x of 3 integral minus infinity to infinity del of t minus 3 dt, correct?
Yes, ma'am.
Call this as t prime, call this as t double prime. You can evaluate this to be 1 and you can also evaluate this to be 1. Which or otherwise you can use the property that integral minus infinity to infinity del of at plus b dt is nothing but 1 by mod a. You can also use this property. Uh, you can also prove this, okay? I think we proved in our last live sessions this part. So this is nothing but x of minus 1 minus x of 3, correct?
Yes, ma'am.
And now what is your x of minus 1? X of minus 1 is 2 minus x of 3 is minus 1, which is 2 plus 1 equal to 3. Yeah,
Yes, ma'am. Yes, ma'am.
yeah.
Yes.
So that is what it is. So what was your confusion in this?
This I didn't know this formula. I lost
Yeah. So all you
this
have to
in
use
calculation.
is the known property of the delta function. Okay.
Yes, ma'am. I cannot use this, so I long
Yeah.
term.
Yeah. So I can also do another problem to help you guys use that property. So eighth question. It is integral minus infinity to infinity del of t e power minus j omega t dt. So this is same as integral minus infinity to infinity j omega t del of t minus 0 dt. So t naught is equal to 0. So this is x of t. So this is integral minus infinity to infinity x of t del of t minus t naught dt, which can also be written as integral minus infinity to infinity x of t naught del of t minus t naught dt, right? So this is simply integral minus infinity to infinity x of 0 del of t dt because our t naught is 0. And what is x of 0? Minus infinity to infinity e power j omega 0 del of t dt, which is nothing but 1, right? So the property all you have to use is x of t del of t minus t naught is equal to x of t naught del of t minus t naught. So this is what you have to use. And integral minus infinity to infinity del of t dt is equal to 1, or integral minus infinity to infinity del of at plus b dt is equal to 1 by mod a. Okay, so these are all the properties of delta functions which you guys, have to just learn them. Okay, is that all right?
Yes, ma'am.
Yeah, any more questions?
No.
Yeah, so yeah, doubts from week 1 to week 4, graded assignments, practice assignments, lecture videos. Okay, so you have to. And Prabhanjit, so I think I have told enough number of times, asking you guys to let me know if you have any doubts regarding these weeks. I think for the last 2 weeks we were discussing only on these topic doubts. So without going through those live session videos, I think it's not a good idea to, you know, ask for more time in today's live session. So I advise you to follow up on the live sessions regularly so that you'll be more comfortable in the course. Yeah. Even others, whoever are not attending the live session. So before attending today's live session, it's better to check if the topics were already discussed in the earlier live sessions. If those things were not discussed in the earlier live session, then you can ask them in the current live session. But yeah, I would not like to uh, spend more time on the same topics that were already discussed. Yeah. Any more questions? For Saturday's live session, uh, I don't know if I should spend more time again on week 1 to 4, because then you guys won't get the time to cover the property like convolution. And without knowing the property like convolution, it would be pretty hard for you guys in the later weeks. So I am not planning to take, another live session. I'm not planning to give another live session for week 1 to 4. Week 5, I would like to spend more time on convolution. If you guys have any questions regarding your quiz topics, please email me those questions. I'll reply to you guys. For the next 4 days, I'll be active on emails. If you have any questions, you guys can email me. So, any of the following email IDs. Multiple times I wrote this up, but you can also post on the group. Next live session, I'm planning to take on the week 5 content. Yeah.
Man,
Yeah.
could you explain the phasor topic once again?
Yeah, sure. So any specific question for you in the phasor topic, or you just
Um,
want
no, no. In magnitude and phasor plots, I am little bit confused.
okay, all right. So what is a phasor? So the phasor is something that is written in the form e power j theta form. So this is also this can also, so you can state m times, so the amplitude times uh, m e power j theta. This is also this can also be written as m cos theta plus mj sine theta. Okay, and the phase is nothing but theta. So phasor is something that is used to represent a complex valued signal. And what is a complex valued signal? So any signal that is of the form xr of t plus j times xi of t. So any signal of this form is known as a complex valued signal. And for every complex valued signal, we have an equivalent representation as a phasor. And how would we do that? So m is nothing but square root of xr of t square plus xi of t square. This is m of t. And theta of t, the phase. So this is the magnitude, and this is the phase. So phase is tan inverse of xi of t divided by xr of t. Okay, so yeah, so for every x of t, there is an equivalent phasor representation which we denote by e power j theta of t. Okay, and now when you have to plot the magnitude and phase plots, let me open up the lecture notes once, just to not get just to so when you want to plot the magnitude and phase plots, the magnitude plot is straightforward. So you just have to calculate the magnitude, x plus xi square of t and the square root of this. So this you can plot in a straightforward manner, right? So because this is always greater than 0, this is always greater than 0, and the square root exists, and you just have to plot. You just have to find the signal m of t and then plot it across the t. The difficulty, I think, comes only when you're planning to plot the phase plot, because The reason for that is, so you're trying to plot tan inverse of the function xi of t divided by xr of t. Okay, so when you plot this, so the phase wrapping, there's something known as phase wrapping. So you have to plot this function very carefully because you're plotting an inverse trigonometric function, tan inverse xi of t by xr of t. The whole idea over here is, uh, so let me just, so the whole idea is tan inverse of theta is nothing but tan inverse of 2 pi plus theta, right? Because, yeah, because tan theta, maybe this is not, tan inverse of x is same as tan inverse of 2 pi plus x. This is I think is correct. So idea that you have to use is, sorry, I think this isn't true. Tan, so the it should be there in our earlier live session, but yeah, I don't have the notes in hand. The So the idea is tan theta is equal to x. So theta is equal to tan inverse x. And tan 2 pi plus theta is also x. So 2 pi plus theta is same as tan inverse x, right? So the idea is theta is same as 2 pi plus theta when you are plotting the tan inverse x function. Is that what it is? 2 pi, or in other words, tan pi plus theta, right? Tan pi plus theta is minus tan theta, which is equal to minus x. So what you can also say is, um, yeah, or let's just put it this way. So theta is same as 2 pi plus theta. So what you can do is, so as you plot across t, if t is exceeding, if it is more than 2 pi, so if the, so while you are plotting, uh, so let me call this phase of t. So if your phase of t is larger than 2 pi, right? So suppose if it is, so phase of t is some 2 pi plus some little x prime. So then you can instead plot this to be as x prime. Okay. So instead of, if it is exceeding more than 2 pi value, okay, so it can either lie in between, so your phase plot can either lie in between minus pi to pi or 0 to 2 pi. Any phase plot is a valid plot. So if it is in between 0 to 2 pi, what you can do is, if the phase value, if your phase of t is larger than 2 pi, I mean if your phase of t is something 2 pi plus some x prime, your phase of t can be considered as just an x prime value. Okay, so that is what. So the way you can do this is, you can just plot the phase function first. So if your phase plot is something like this, suppose if your phase is just t, so phase of t is just t, then what you have to do is till 2 pi, you're okay. But after 2 pi, what happens is the phase gets wrapped, right? So after 2 pi, it is again 2 pi plus some t prime, and t prime would be something like this until 4 prime, you will get like this, and then again like this. Similar thing happens here. Okay. So the idea is this. So tan 2 pi plus theta is same as tan theta. Okay. So that is the idea. Or otherwise, tan pi plus theta is also tan theta. Okay. Uh, so tan pi plus theta is also x. Pi plus theta is same as tan inverse x. Uh, which is, so if tan, uh, yeah, if this is x, then tan pi plus theta uh, is tan inverse x, which is theta. So every pi plus theta can be replaced by a value theta. Okay. So that is the idea that we use here. Okay. Is that all right?
Yes, ma'am.
Yeah. So,
Yes, ma'am.
uh, so for the magnitude plot, you don't have any difficulty in plotting the magnitude plot. You just have to find the magnitude, which is x r square of t plus x I square of t, and then plot as it is. So this is just a function of t. It's a signal, and you have to plot that signal. But the difficulty arises, it's not even the difficulty. You're trying to bound the phase, because tan inverse function is lying in between either minus pi to pi or 0 to 2 pi. Anything is fine. I just showed you a plot that lies in between 0 to pi. Either the function value is 0 or it takes a value 2 pi. Okay, I'm upper bounding it by 2 pi. There's also a separate discussion where the professor lower bounds it by minus pi and he upper bounds it by plus pi, which is also a valid thing to do for the phase plot. But the whole idea is, when you take the tan function itself, suppose if your tan theta is x, your tan 2 pi plus theta is also tan theta, remember? So this will also be x, right? So your x is, so your tan inverse x is theta, and your tan inverse x is also 2 pi plus theta. So any 2 pi plus theta can be replaced by a value theta. So that's the whole idea. And the wrapping is a technique. So suppose if you have a phase plot, uh, phase of t is just t. Okay. So this is your phase plot. So it's just a t. So if you have something like this, what you do is, uh, or simply I'll take the positive t. T when t greater than 0, 0 when t less than or equal to 0. So suppose if you have a phase plot like this, so how do you wrap? So you have 2 pi plus theta equal to theta, which is here we are using t. So 2 pi plus t is simply t. So this is your t, this is your phase of t. So till 2 pi you're okay. Okay, but after 2 pi, so the first value after 2 pi would be 2 pi plus 1. So 2 pi plus 1 is just 1. So it keeps increasing again till 4 pi. Okay, and again increases till 6 pi and all. Similarly, likewise on the other side. Okay, I hope this is clear. So this technique is known as phase wrapping. So you just have to wrap it between the you know uh, values, either 0 to 2 pi or minus pi to pi, both are valid techniques. So here I am talking about 0 to 2 pi. Okay, minus pi to pi, you can refer to the lecture video. So both are valid techniques. It's the same idea. Okay. So
Okay.
if you have minus pi to pi, it'll again be the same plot, no difference in the plot, but I think your lower value will be minus pi and the upper value will be pi, but the values remain the same. Okay, you can check this up in the lecture video, but 0 to 2 pi is also a valid plot to do. There are multiple ways to wrap. I just helped you in solving this step. Okay. Yeah. Yeah, good. So I'm here for 5 more minutes. Any questions?
Are you planning to release a pre-quiz test? I mean,
There is no
hello?
pre-quiz for this course because I think we gave enough number of practice assignment questions. Uh, like I said in the previous live session, the quiz contains 20 questions, 2.5 marks each, and 20 questions are very similar to your assignment questions. So we are not planning to release any pre-quiz. Okay.
Okay.
Yeah. Any more questions? So I think in your minus pi to pi case, you have to use the following. Tan pi plus theta is same as, so is tan minus t minus theta minus tan theta or what? Hmm, or tan theta, that I don't know. So I am I get confused with this minus notation. That's the reason why I try to use 0 to 2 pi plot. Yeah, you can refer to the professor's notes maybe. I don't want to confuse you guys. Yeah. All right. Any more questions?
No, ma'am.
Yeah. All right. So can we end today's live session?
Yeah. Thank you.
Thank
Yeah.
you, ma'am.
So if you have any questions related to uh, the week content, please feel free to email me. But yeah, next Saturday's live session, I'm planning to take on week 5 content. Okay. Yeah.
Okay.
Thank you. Thank you.
Thank you, ma'am. Good night.
Yeah.
Thank
Thanks.
you,
Good
ma'am.
night.
Thank you, man.
Yeah. Good night. Good night.
Good
Good night.
night.
Yeah.